Hello.
Hola. Ok. Espera, això no ho fa. Okay, so as I have said, today I'm going to talk about numerical methods for quasi-stationary distributions, and this is a project that I have done with Javi Aguilar, Tobias, and Raúl. First of all, I'm going to show some examples of stochastic models with absorbing states. An absorbing state is simply a state from which the system cannot escape. So if the system enters into an absorbing state, it will remain there forever. We will see that the decay towards absorbing states can be used to model a lot of phenomena, as for example, the fading of diseases, consensus in opinion dynamics, or the extinction of a species. I will show you that in the study of stochastic processes with absorbing states, we can get a lot of information from the distribution of the process conditioned to never get absorbed, which is called the quasi-stationary distribution. And I will show you two numerical methods that we have developed to obtain the quasi-stationary distribution. So first of all, let's see some examples of stochastic models with absorbing states. And of course, I'm going to start with the water model. In the water model, we have a population of n individuals, and each individual can hold opinion A or opinion B on a given topic. And our stochastic variable is the number of individuals in state A. In this model, if an individual holding opinion A and an individual holding opinion B interact, this can make the individual holding opinion B to switch to opinion A at rate HA, or it can make the individual holding opinion A to switch to opinion B at rate HB. So in this model, there are two absorbing states: the state in which all individuals are in a state A, and the state in which all individuals are in a state B. Because in these two situations, changes of opinion don't happen anymore. So if the system enters into one of these two states, the system will remain here forever. So these are two absorbing states and are states of consensus. Now we can look at the susceptible infected susceptible model, or SIS model. This model describes a population of n individuals, and each individual can be infected by a specific disease or healthy and therefore susceptible to get the disease. In this case, our stochastic variable is the number of infected individuals. And in this model, if a susceptible individual and an infected individual interact, the susceptible individual becomes infected at rate beta, and on the other hand, infected individuals recover from the disease and become susceptible again at rate gamma. So in this model, there is one absorbing state, which is the state in which all individuals are susceptible, because in this situation, infections don't happen anymore. So if the system enters into this state, that is an absorbing state, the system will remain here forever and the epidemic will be extinct. Okay, so now let's look at the dynamics of the SIS model. That is, let's see how is the evolution of the probability of having n infected individuals at time t. So imagine that we start, our initial condition is that we have some specific number of infected individuals n0, so that the initial probability distribution is a Dirac delta centered around this value. Here we will have some dynamics, the system will evolve, but what is sure is that eventually, at some time, because since the dynamics is stochastic and there are no forbidden states, at some point the system will fall into the absorbing state and the disease will disappear. So it's clear that the stationary probability distribution of this model is a Dirac delta centered around the absorbing state, which is the state with no infected individuals. So the end of the story is clear. The disease at some time will disappear, but the question is, how long does it take for the disease to disappear? So to answer this question, we have to look at the transmission factor, which is the ratio between the infection rate and the recovery rate. If this transmission factor is smaller than 1, what means that the recovery rate is larger than the infection rate, In this case, individuals recover fast from the disease, and the disease will decay, starting from any initial condition, the disease will disappear very fast, in a very short time. But if this transmission factor is larger than 1, the situation will be very different. In this case, starting from some initial condition, the system will, in some initial transient, will evolve and will enter into a metastable endemic state. In this metastable endemic state, the number of infected individuals fluctuates around a fixed quantity. But as we know that the dynamics is stochastic and there are no forbidden states, at some point, this disease will disappear because the system will fall into the absorbing state. In this case, the mean time needed for the disease to disappear increases exponentially with system size. So in some cases, this absorption time can exceed the age of the universe. So it can be really, really long. Okay, so this intermediate regime in which the system fluctuates for a very long time around the metastable state is called the quasi-stationary regime. And this regime gives us a lot of information about the process. So if we are interested in studying this quasi-stationary regime, where the system fluctuates in the metastable state for a very long time without touching the absorbing state, if we want to study this regime, what we can do is to study the process conditioned to never get absorbed. The dynamics of this process will be, we start from some initial condition, we evolve into this quasi-stationary regime, but unlike in the original process where the process can die, the process can get absorbed, in this auxiliary process, we don't let the system to get absorbed. So in this case, this process will remain in this quasi-stationary regime that we want to study forever. So the stationary distribution of this process, which is called the quasi-stationary probability distribution, describes this quasi-stationary regime that we want to study about the original process. So in summary, in the dynamics of processes with absorbing states, we have three regimes. We have an initial regime in which the system evolves towards the quasi-stationary regime. Then we have the quasi-stationary regime itself. And then finally, we have a final transient in which the system decays towards absorption. And if we want to study this quasi-stationary regime, what we can do is to study the process condition to never get absorbed. Well, here I would like to say that in the case that the transmission factor is smaller than 1, we have seen that the disease dies very fast. But here I just want to say that in this case, there is also a quasi-stationary regime. It's not that obvious. We cannot see it here very easily. But the process condition to never get absorbed, its probability distribution converges to a quasi-stationary probability distribution. Maybe it makes more sense to talk about a quasi-stationary regime here in a mathematical context than in a physical context. But here we also have a quasi-stationary regime, okay? So now, why are quasi-stationary probability distributions important? Quasi-stationary probability distributions characterize fluctuations in the dynamics towards absorption, so they allow us to obtain different quantities. For example, we can calculate exit probabilities. To talk about exit probabilities, we have to go to a model with more than one absorbing state, as for example, the Botter model. In the Botter model, we have these two absorbing states, and we know that eventually, at some time, we will fall into one of these two absorbing states. So exit probabilities tell us which are the probabilities that the system gets absorbed into a state A or the system gets absorbed into a state B. These are exit probabilities. Thanks to the quasi-stationary probability distribution, we can also calculate mean absorption times. We have seen that in the SIS model, if the transmission factor is larger than 1, that this is called the supercritical regime. So we have seen that in this supercritical regime, the mean time needed for the disease to disappear increases exponentially with population size. So this time can be characterized using the quasi-stationary distribution. And finally, using quasi-stationary probability distributions, we can sample rare events. What are rare events? Rare events are events that have a very low probability of occurrence. For example, in this supercritical regime of the SIS model, as the mean time needed for absorption increases exponentially with system size, for large populations, it's very unlikely to observe the extinction of the disease. So this is a rare event, and if we are interested in sample this kind of events, we can use quasi-stationary distributions. And actually, this is the motivation. The sampling of rare events is the reason for which we started to work with quasi-stationary probability distributions. Okay, so now I'm going to define the quasi-stationary distribution, and I'm going to start with the simplest case, which is a stochastic process with continuous time and discrete states. This process will be characterized by some transition rates. And at the beginning, I will assume that this process only has one absorbing state, the state 0. So it could be, for example, the case of the SIS model. If the state 0 is absorbing, this means that all transition rates that go out from a state 0 are 0. So if the system enters into the state 0, it will remain there forever. The evolution of this process is given by this master equation, where here we have the evolution of the probability that the stochastic variable takes the value n at time t, and we can see that the master equation has two terms. The first term here represents the probability flux going out from a state n, so it has a minus sign, and the second term represents the probability flux going into a state n, so it has a plus sign. And if we want to write this equation in compact vector form, we can do it in this way. Now here P is a vector whose components are the different probabilities in the different states, and this L is the transition rate matrix, which is a matrix that contains all the information that we have here on the left. So now we want to obtain the quasi-stationary probability distribution of this process to characterize the quasi-stationary regime. So what we can do is to study the process conditioned on non-extinction. We want to study the process conditioned to never get absorbed. And we will denote the probability of this process with a letter Q. So in this process, the probability that the stochastic variable takes the value n at time t is the probability that the stochastic variable at time t takes the value n, given that the stochastic variable is different from 0, because we don't want this process to fall into the absorbing state. This state is forbidden here. So this probability will be 0 for the absorbing state, of course, because we don't want to fall into that state. And for all the other states, for state 1, 2, 3, up to n, this probability is identically the same as in the original process. I mean, the probability Q is equal to the probability P, but for normalization, we have to divide it by 1 minus P of 0, okay? So the equation for the evolution of this probability Q is this one. And what we see here is that these first two terms are identical. You can see that are identical than in the original master equation. But now here we also have a new term, okay? In this term, we have the probability Q multiplied by this sum here, and this sum here represents the flux into the absorbing state 0. So this term, what is telling us is that the probability flux that in the original process goes into the absorbing state, in this process, this flux is redistributed among all the other states. And you can see that this term is nonlinear because we have a Q multiplied by Q. So this term is nonlinear, and in compact form, we can write it in this way. This first term with the transition rate matrix is identical than in a master equation. This is the same transition rate matrix. And we also have here a nonlinear term with the flux into the absorbing state. We have said that if we want to obtain the quasi-stationary distribution of this process, what we have to do is to study the stationary distribution of the process conditioned on non-extinction. So the quasi-stationary distribution is the stationary solution of this distribution, so is described by the equation that we have here. So in summary, if we have a discrete process with a single absorbing state at 0, we have that the quasi-stationary distribution is 0 at the absorbing state and is the solution of this nonlinear equation for all the other states, where here this J0 is the flux into the absorbing state. So now, if we consider a stochastic process with two absorbing states, one at 0 and one at n, as it can be, for example, the case of the water model, if we repeat all the procedure that we have done, what we see is that the quasi-stationary distribution has to be 0 at the absorbing states because we don't want to touch them. And for all the other states is the solution of this equation, where now the nonlinear term includes the sum of the fluxes into the two absorbing states. So with these results, we can easily generalize these results to a discrete stochastic process with an arbitrary set S of absorbing states. In this case, what we have is that the quasi-stationary distribution is 0 for all the absorbing states, and is the solution of this nonlinear equation for all the non-absorbing states, where now here this J sub S is the sum of all the fluxes into each of the absorbing states. Okay. So now I will also define the quasi-stationary distribution for a continuous process. In this case, I will not consider a completely general continuous process because I don't want to make this too boring. So I will just focus on the case in which this continuous process has an absorbing state at the origin. So we have a stochastic process with continuous time and continuous states. Our stochastic variable can move in the interval between 0 and L, and we assume that the state 0 is absorbing. This process is described by the Fokker-Planck equation, where we have the drift term and the diffusion term, and in compact form we can write it in this way, where now here the L, this L is the Fokker-Planck operator. And in this kind of processes, the probability flux into a state X is given by this equation. So if we want to obtain the quasi-stationary distribution of this process, we have to study the process conditioned on non-extinction, the process conditioned to never get absorbed. In this case, the situation is very similar as in the case with discrete states, but the difference is that now this Q is not a probability, but is a probability distribution function. So that Q of X multiplied by dx is the probability that the stochastic variable takes values in the interval between X and X plus dx, given that, this is the important thing, given that the stochastic variable is different from 0, because we don't want to fall into the absorbing state. Well, here the flux is defined in this way, and in this case, the evolution of Q is given by this equation, where again, these first two terms are identical than in a Fokker-Planck equation. But here we have a new term that contains the probability Q multiplied by the flux into the absorbing state. So again, in compact form, we see that here now we have two terms. The first term is identical as in a Fokker-Planck equation, and we have a new term which is nonlinear because this flux J depends on Q. So we have Q multiplied by Q. And we know that the quasi-stationary distribution is the stationary solution of this equation. So the quasi-stationary distribution is described by this equation. Okay, so now we have defined the quasi-stationary distribution. So let's see how we can obtain it. First of all, in some situations, it's possible to obtain the quasi-stationary distribution analytically, but this is only possible for very few models and very simple models. So sometimes we can use analytical approximations, but usually they are very difficult to understand or to implement. And sometimes they don't describe correctly the tails of the distribution. So it's very common to use numerical methods to obtain quasi-stationary distributions. And in particular, iterative algorithms and simulation methods are very popular techniques. The problem is that the existing methods in the literature are restricted to particular families of processes. It's very common to find methods that allow us to obtain the quasi-stationary distribution of a discrete process with an absorbing state at 0. But if you only focus on this kind of processes, you are missing a lot of processes. So we thought that it could be a good idea to develop some numerical methods to obtain the quasi-stationary distribution of a completely general Markov stochastic process. So, first of all, I'm going to present you an iterative algorithm that we have developed to obtain, first of all, I'm going to focus on the case of a discrete process with an arbitrary set of absorbing states. Remember that in this case, the quasi-stationary distribution is the solution of this nonlinear equation with this, where this J sub S is the flux into the set of absorbing states. So if we take this equation here and we rearrange terms, we get this expression here. And remember that this expression is valid for all non-absorbing states, because we know that for all absorbing states, the probability Q is 0. So what we want to do here is determine numerically this probability Q. We want to obtain this Q numerically. So what we can do is to take this relation and iterate it. So we propose an initial guess for the quasi-stationary probability distribution. For example, we propose a uniform distribution, and then we take this relation here and we iterate it. Here we have this case represent the algorithm step number. So this means that I start with my initial guess Q0. From Q0 I get the Q at the next step, Q1. From Q1 I get Q2, and so on. And we repeat this procedure until we reach convergence. The problem is that if we keep the algorithm in this way, sometimes this doesn't converge because we enter in an infinite loop and it never converges. So to fix this problem, we apply over-relaxation, which simply consists on modifying the iterative relation in this way. We add this new term here and we multiply it by A, which is called the relaxation factor, and we keep this previous term in the same way, but we multiply it by this term here. And this relaxation factor is between 0 and 1. So we iterate this relation until we reach convergence. In particular, our convergence criterion is this one. This is like a measure of the distance of the distribution that I have at one step and the distribution that I had at the previous step. So when this distance is smaller than 10 to the minus 10, we affirm that the algorithm has reached convergence. So now let's apply this iterative algorithm to some examples. First of all, I would like to start with an example for which we know the analytical solution of the quasi-stationary distribution, so we can compare our iterative algorithm with the analytical solution. I'm going to start with this branching process. This branching process describes a stochastic population in which particles can reproduce and can die. Our stochastic variable is the number of particles, and the state 0 is absorbing, because of course, if there are no particles can die or can reproduce. In this model, the schematic reactions are these ones. We have the birth reaction at rate lambda and the death reaction at rate mu. Here we have the corresponding transition rates, and we can define the reproduction factor, which is the ratio between the birth rate and the death rate. In this model, if this reproduction factor is larger than 1, the population will grow indefinitely. So we have unlimited growth. This process doesn't have a stationary distribution, so we are not interested in this case. We want to study the case in which the reproduction factor is smaller than 1, because in this case we will have a quasi-stationary regime. The process converges to a quasi-stationary distribution, and we have the analytical expression for the quasi-stationary distribution. So here we have the results of the quasi-stationary distribution of this model for different values of the reproduction factor. And these different symbols represent the results from the iterative algorithm, and continuous lines correspond to the analytical solution. So we can see that this algorithm works very well. So now we can apply this algorithm to the SIS model. Here we have the schematic reaction, the transition rates, the transmission factor. And here we have the results of the quasi-stationary distribution for different values of the transmission factor. So, for example, if we are in the supercritical regime, that is, if the transmission factor is larger than 1, as it can be this green curve here, what we see is that the quasi-stationary distribution is centered around the metastable endemic state in which the system spends a lot of time before it goes to the absorbing state. But if the transmission factor is smaller than 1, that in this case the disease dies very, very fast, so in this case the quasi-stationary distribution is centered around the absorbing state, which is 0, the origin, the state with no individuals. Okay, if we apply this algorithm to the Botter model, well, here we have the schematic reactions of the Botter model, the transition rates, and here we have the quasi-stationary distribution for different values of this ratio here. The ratio at which individuals go to opinion A and the rate at which individuals go to opinion B. So we can see that if this ratio is equal to 1, we have a flat distribution because we have the same probability of being into both states. But if this ratio is larger than 1, the quasi-stationary distribution is centered around the absorbing state of consensus in A. And if this ratio is smaller than 1, is the opposite. We have the quasi-stationary distribution centered around the state of consensus in opinion B. Okay, sorry, what I wanted to say here is that, look, we have to look that this model has two absorbing states. So most of existing methods, numerical methods in the literature, with that methods, we couldn't obtain the quasi-stationary distribution of the Botter model because that methods usually are restricted to processes with a single absorbing state. So that's a good thing about our iterative algorithm. And finally, and very fast, the last example is another stochastic population model. Again, the number of particles is denoted by the letter N. The state with zero particles is absorbing. And in this process, in this model, we have the birth and death reactions as before, as in the branching process that we have seen. But now we also have an annihilation process. And this annihilation process is a two-step process because I start with 2 particles and then I have 0 particles. So this is called a two-step process. So again, most of the existing methods don't allow us to calculate to obtain numerically the quasi-stationary distribution of models with 2-step processes because sometimes, most of times, they are restricted to 1-step processes. But again, we see that with this iterative algorithm, we can obtain the quasi-stationary distribution of this model. So now, maybe this is very ugly, I know, but now I'm going to explain very, very quickly how we can apply this iterative algorithm to obtain numerically the quasi-stationary probability distribution of a continuous process with a single state at the origin. So remember that in this case, the quasi-stationary distribution is the solution of this nonlinear equation. Here we have the equation in compact form, and here we have the extended version, let's say. And this J0 is the flux into the absorbing state, 0. So if we want to apply an algorithm to solve this equation, first of all, we have to discretize a space. So we discretize a space. I will not go into too much detail, okay? We discretize a space. And then we obtain these relations, these iterative relations. These iterative relations are the result of taking this equation here and discretizing it using center derivatives for all the internal points and except for the last point where we apply reflecting boundary conditions and we make backward differences. Okay, I don't want to go into the details, but we have this scheme here, so we can propose an initial guess for the quasi-stationary distribution, and then we can iterate these equations until we reach convergence. What I think that is important here is that, as far as we know, nobody before had proposed an iterative algorithm to obtain the quasi-stationary distribution of a continuous process. So we think that this is completely new, and maybe you think that this discretization is very easy, but for us, it was very difficult to obtain a scheme a discretization scheme that worked, and this one is the one that worked in this case. So well, here we have the iterative scheme, and if we apply it to a particular example, so let's see what we obtain. Here we have a continuous branching process, that this is a process with these drift and diffusion functions, and this is the corresponding Ito process. We can see that the state 0 is absorbing, because if we introduce here x equal to 0, we have that the equation for the evolution of x is 0. So the dynamics stops. And here we have the results of the quasi-stationary distribution. In this case, we also have the analytical solution of the quasi-stationary distribution, which is, I think you cannot see it very well, but with solid lines, we have the analytical solution, and with dotted lines, we have the solution of the iterative algorithm. So in this case, we also get very good results in the continuous case. So now that we have seen an iterative algorithm to obtain the quasi-stationary distribution, I'm going to tell you another technique to obtain this quasi-stationary distribution. Again, we find that the methods in the literature, or they are restricted to particular families of processes, or sometimes they incorporate too many parameters. And in this case, what we wanted to do is to make a Monte Carlo simulation method as simple as possible. And the idea is the following one. First of all, I'm going to explain it for a discrete process with an arbitrary number of absorbing states. So imagine that we have this process here. This is a discrete process, and we have states 0, 1, 2, 3, 4, and 5. And let's imagine that states 0 and 5 are absorbing. So what we will do is to make a single realization. In a single realization, we will do a single realization of this process, but very long. Okay, so at time 0, we start the process in a non-absorbing state, for example, state 2. And then what we will do is that we will let this process evolve using, for example, the residence time algorithm. And during all the simulation, what we will do is to store or to accumulate in a histogram the time that the process spends in each of the different states. So, for example, we start here at time 0 in state 2, and now we are going to start the process. We see that after a time t1, the process jumps into a state 3. So this means that the process has spent a time t1 in state 2. So we add a quantity t1 to the component 2 of this histogram, okay? Now we are in a state 3, and we see that after some time t2, the process jumps back into a state 2. That is, the process has spent a time t2 in a state 3, so we add this quantity to the vector, okay? We are now in t2, after some time t3, we jump into a state 1, okay? And now we are in a state 1, and after some time t4, the process wants to jump into the absorbing state. So now, what we will do is to reset this process, because we don't want this process to die. We don't want this process to get absorbed. So we will go to all the non-absorbing states, and we randomly will choose one of these states, taking into account the histogram weights. So in this way, it will be more likely to reset the process in the states in which the process spends more time. So we randomly have to choose one of these states, taking into account the histogram weights. So for example, we randomly choose state 3. So we place the process in a state 3. In this way, what we are doing, if we keep doing this procedure, what we are doing is that we are simulating the process conditioned on non-extinction, because we are not letting this process to die. And we know that the stationary probability distribution of the process conditioned on non-extinction is the quasi-stationary probability distribution. So if we repeat this procedure for a very large number of steps, this histogram here will converge to the quasi-stationary probability distribution. If we want to do this simulation method for a continuous process, the idea is practically the same. The only difference is that, first of all, we have to discretize space in some bins, okay? So the idea is the same. We will start the simulation in a non-absorbing state, then we will let the process evolve. In this case, we will use, for example, the Euler-Maruyama scheme, and then each time we will accumulate a histogram with the time that the process spends in each of the different bins, okay? And if the process is absorbed, we will randomly select a bin, and then we will randomly select a position within that bin, and we will place the system into that state, okay? And again, after a very large number of steps, the histogram will converge to the quasi-stationary distribution. Here we can see some examples of this Monte Carlo simulation method. We start with discrete states. We have the branching process, the SIS model, and the water model. In the case of the branching process, we have the analytical solution with continuous lines, the solutions of the iterative algorithm that we have seen before with symbols, and the black crosses represent the results of the Monte Carlo simulation methods with 10 to the 9 simulation steps. And we can see that results fit very well. And for the SIS model and for the water model, we don't have analytical solution, but we can also see that the results of the iterative algorithm and of the Monte Carlo simulation method fit very well. Finally, we can also see the application of this Monte Carlo simulation method to this continuous branching process. Here, I'm sure that you cannot see nothing, but we have that the analytical solution, the solution of the iterative algorithm and the solution of the Monte Carlo simulation method are on top of each other. So the results, again, are very good. And to finish the presentation, very quickly, I would like to go to multidimensional problems. Very quickly. So imagine, for example, that we have a Brownian motion in 2 dimensions. That is, we have this Brownian motion here, both in the X and Y direction, where here this R is the radial variable. So we have this Brownian motion in this donut, and we have a reflecting boundary outside and an absorbing boundary inside, okay? If we wanted to apply the iterative algorithm to this problem, well, I don't know, we don't know how to do it because we have a 2-dimensional problem, we have to discretize an equation for a 2-dimensional problem, we have here a reflecting boundary and an absorbing boundary. I think that would be impossible. But with the Monte Carlo simulation method, it's very easy to simulate the quasi-stationary distribution of this process because the only thing that we have to do is to advance in time both the variable X and the variable Y, and we make a histogram, a 2-dimensional histogram of the time that the particle spends in the space XY. And then at each step, what we do is to check if the variable R has crossed the absorbing boundary, and if the variable crosses the absorbing boundary, we reset the process into some point in this donut, okay? So here we can see the solution of the quasi-stationary distribution in 2 dimensions that we get with this Monte Carlo simulation method. And as this problem has a spherical symmetry, we can also think about this process as a 1-dimensional problem. So we can also obtain a histogram of the radial variable. And in this case, we can compare our results with the analytical solution, which we know it. And we can see that, again, results are very good. So in summary, we have seen that in models or processes with absorbing states, it's very useful to work with the quasi-stationary distribution because it gives us a lot of information. We can calculate mean absorption times, exit probabilities, we can sample rare events. We have seen that this distribution is the solution of a nonlinear equation, where here we have a term with the flux into the absorbing states. And we have seen the two methods that we have developed to obtain the quasi-stationary distribution for a completely general Markov stochastic process. We have seen an iterative algorithm and a Monte Carlo simulation method. And we have seen that in both cases, we can consider a process with continuous or discrete states. We have seen that these processes can have an arbitrary number of absorbing states. And finally, my final conclusion for the difference between these two methods is that the iterative algorithm is very easy to implement and it converges very fast. But I think, so I prefer this algorithm for processes in one dimension, but I think that the Monte Carlo simulation method is a very good option for processes in more than one dimension, because in this case it's very easy to implement. Okay, so that's all. Thank you.
Thank you. Any questions or comments?
Thank you very much. I have tons of comments and questions. Because although I'm now a bifurcation boy, I'm really interested in these methods. And first, a comment that is congratulations, because for me it's very hard to give a talk, such a technical talk, in a very crystalline clear way, and you have done it. So thank you very much. First comment is that I really like that this approach to characterize quasi-stationary distributions, because in the ecological world, modeling world where I come from right now, there's now a trending topic, which is transients. So transients basically mean quasi-stationary states, and they have no way to define them because they always work in the deterministic regime. And I really like to see that there's a clear formal way of characterizing a quasi-stationary regime of distribution with the probabilistic approach. Mm-hmm. So my first question is about the analytical results of some of them, or well, the few they may be. They provide some insights on the, for instance, the survival times, or they provide useful information, these analytical results. For instance, survival times and the size of the fluctuations and things like that. They provide this kind of information. Are they useful? Is my question.
Well, if you, for example, about the mean absorption time and so on, I know that there are analytical approximations to these times for some models. Right now, as our principal interest about this project is not to work with mean absorption times, but is to sample rare events. I'm not that much into this topic. The only thing that I can say is that for some models you can obtain analytical approximations of the mean absorption time. And well, about the fluctuations, if you have, for example, here we have the analytical solution. This is giving you information about fluctuation. So and you can have if you have the analytical distribution, you have the information about the fluctuations around the absorbing state. But about the mean extinction time, right now, Raúl, I'm sure that he knows. If you have the analytical distribution,
okay.
Whether it's exponential in system size.
Okay. Thank you. I have more questions. It's like, perhaps this is a full question, but what about there are no absorbing states? I'm thinking in the Botter model with Silox, or the noisy Botter model, which has some quasi-stationary regimes in which is very close to a virtually absorbing state if there were no Silox or there were no noise. So it spends a lot of time near some absorbing state fluctuating, but it is not an absorbing state. Do you think there is a kind of a similar approach to estimating those distributions?
Well, I don't know, because in that case,
You cannot define
because
all of
we
these.
are all our work is based on the study of a process conditioned on non-extinction.
Mhm.
But if the process cannot get absorbed, these
Yeah.
two processes would be the same.
Yeah, of course, of course.
Yes,
I know it's a tricky question. My question is if you think there could be some similar methodology.
There's no question, right? Stationary.
Yeah, of course. Yeah.
Yeah.
Yeah, it's right. It's right. Yeah. I knew this was going to be a full question. And well, and do you have some insight of why this iterative method should work? I mean, if I have to solve the quadratic formula, I do not apply iteratively the quadratic formula.
A lot of problems are solved in. No, actually, I think it's magic. No, I don't. A lot of problems behave in this way.
I mean, I also use iterative methods, but you usually have a rule. You define the rule in some semi-formal way. I'm thinking in the Newton-Raphson method, and I also was about to ask if Newton-Raphson method, multidimensional Newton-Raphson method, could be applied here for solving nonlinear equations. As I use the multidimensional Newton-Raphson method to solve nonlinear equations.
Well, at the beginning, because more quickly, where do we have? At some point, because I have said that if we keep the iterative relation in this way, we enter in an endless loop, and then we could fix the problem by using this over-relaxation. So I remember we discussing with Raúl about this Newton method and so on, but as we could fix the problem in this very simple way, so because you can see that this method is very, very simple. I mean, you just have to take this relation and iterate it. So if this method works,
yeah,
we didn't need to go to other methods.
Yeah, yes.
So we did not understand it for us.
También.
And
You can illustrate us.
and my final question is, can you go to the slide with the Botter model, the results for the Botter model? So I don't know exactly the number. I should have written it down.
This one.
Yeah, that one, of course. I was looking at the plot, and it reminded me of the stationary distribution of the Botter model. Just you have cut the absorbing states. I mean, the critical one is flat, and the others are unimodal. So my question is, and remembering the first definition you give of the quasi-stationary probability distribution, which is to rescale the original one, why cannot you get these distributions from the original definition? So you get first the stationary one, which is easy in the Botter model, and then you rescale it.
You are saying that the difference of that in this process, the thing that we are doing is to take the flux into the absorbing state and redistribute it among the other states.
Yeah, but
so you say is to know if I understand your question.
Perhaps it's more useful to go to the original formula in which you define the quasi-stationary probability distribution. Yeah, there. So perhaps I'm losing the point here, but I remember that what I'm seeing here. My question is: could you obtain the regular stationary distribution, and just rescale it with that law in the setting zero the absorbing states and rescale?
But in this model, the stationary distribution is for example, in this Botter model, in this Botter model with no noise, the stationary distribution would be the combination of two Dirac deltas around the two absorbing states.
Yeah.
So from there you cannot get.
Right. I was, of course, yeah, that I was missing. I was confusing the distributions with the ones of the noisy Witten model I have worked with. Yeah, that was my mistake. Okay, so well, thank you very much. I'm sorry for many questions.
No.
Questions or?
I have a question about how would you sample exactly rare events of the quasi-stationary distribution?
Here I have
That's a different talk. Nice.
wow. This is a recycled from my master thesis. So to sample rare events, what we use is a method that developed Raúl, Tobias, and Javi, which consists of, okay, imagine in blue, what we have in blue is some realizations about a stochastic process, conventional realizations. We have a stochastic process, we set the initial condition at x0 and we let the process evolve, and we see that trajectories end at any point, no, here. So now imagine that we want, what we do to sample rare events is, for example, imagine that we have said that in the SIS model, in the supercritical regime where the system fluctuates around the metastable endemic state for a long time and it's very unlikely the disease to disappear. Do you remember? So in this case, the rare event consists of going from this metastable state to the absorbing state. This is the rare event that we want to sample, no? From the metastable state to the extinction of the disease. So what we do to sample this rare event is to construct what are called stochastic bridges. We construct bridges that go from this point to this other point, okay? And these bridges have the same statistics of the original process and keep the statistics, no? So what we do is to sample these bridges going backwards in time. Instead of starting in the metastable endemic state and finishing in the absorbing state, we start in the absorbing state and we go backwards in time up to the metastable endemic state. And this is a bridge, and we construct it backwards in time. So for example, in this situation, imagine the original process typically starts in x0 and ends in this region here, typically. And it would be very strange that a blue trajectory of the original process ended here. We don't observe that. So now imagine that this is the rare event that we want to study. We want to study the rare event in which the process goes from here to here. So what we do is say, okay, I will start my simulation at the point where I want to finish, and then starting here, I will go backwards in time. I will construct a bridge going backwards in time up to the initial point, okay? And for doing this, what we do is to use these, we use rates that operate backwards in time. So we start here, we go backwards in time with these rates, and we end here. And the difficult thing about this method is that we need the probabilities of the process. And most of the times you don't have this information. So here is when we approximate these probabilities by the quasi-stationary probability distribution. Because for example, in the case, well, I don't want to go into too much detail, but in the case of the SIS model, here we have the metastable endemic state. When we are in this metastable endemic state, the probability peak is around this state, no? So if we want to simulate paths that connect the metastable endemic state and the extinction state, what we do is that at time t, we place the system at the extinction state, and then if we approximate the probability by the quasi-stationary probability distribution, so it is sure that the bridge will jump into the metastable endemic state. So we will have the bridge that we want. I don't know if maybe the idea is.
Yeah. Oh, and then now I have to process it a little bit.
Yeah, no, because this is, I know that this is.
Yeah, but it's, yeah.
Okay, any other questions? Nothing?
Can you go to the discrete first and depth
Discrete.
to the stationary distribution?
Yes.
The quasi-stationary in the first and
Here.
this is equals to 0 or equals to some value?
Well, in fact, here you can see that this is in the discrete case. So all this point corresponds to state 1. You mean, no, you are meaning.
The n going to infinity equals to 0 or equals to some.
Vale. Yes, to 0.
Okay.
Yes, sorry. Now I didn't. I thought you were talking about this 0. No, you say that the distribution.
No, equals to 0.
Yes.
Okay.
It's a geometry, right? Or
Sí.
background rate.
The analytical distribution.
Questions? If not, we can start again.
Thank you.
We start the recording.
Vale.